A very good morning, ladies and gentlemen. It's my privilege and honor to be delivering the lecture today on the occasion of the Quality Day celebrations of the Vikram Sarabhai Space Center. I'm indeed honored with the invitation given to me, and I do hope as I share my experiences of enhancing and sustaining quality through technology, innovation, and processes, you will find this interesting and useful in terms of deploying some of the concepts to your own applications and your own organizations. At the outset, let me thank Dr. Sarath Chandran and Vikram Sarabhai Space Center and Dr. Gopalakrishnan for kindly inviting me to deliver this talk. I, of course, need to thank a lot of colleagues and team members at the various organizations I have worked at, GE, IGCAR, the Indian Society for Non-Destructive Testing. I have, of course, taken the liberty of pulling out several web resources and to present in this talk, so I acknowledge all those web resources. And of course, in the long journey of 36 years in the professional career, I've met and interacted and learned a lot from several colleagues, thought leaders, and experts. So I've put in some of those learnings also in this particular talk. I would like to start by dedicating this talk to my mentor and guru, Padma Shri Dr. Baldev Raj. Several of you probably know him, have met him and interacted with him. He was the director of Indira Gandhi Center for Atomic Research, after which he also was the director at the National Institute of Advanced Studies, Bangalore. My professional journey started with him in 1984. And since then, until his passing away, he has been my guru and mentor. And it was he who, in many ways, inculcated in me also the desire, the need, and the importance of quality in everything which we do, be it research, be it teaching, be it training, be it giving a lecture or anything. I remember very distinctly that he used to pay so much attention to quality in everything, and he never used to discriminate between a presentation he would make to to the chairman of Atomic Energy Commission or to a college, a group of students in the college. He would emphasize on quality in everything which we share, in everything which we do. So to him, I owe a lot to what I am today. And with that, I dedicate this lecture to him and move on to the actual topic. My career started in the Atomic Energy, Department of Atomic Energy at the Indira Gandhi Center for Atomic Research, Kalpakkam in the 1984. And that was a time when, the technology wasn't so advanced as to what you see today. Almost everything was analog in nature. There were hardly any computers. We used to work on mainframe computers. So everything was quite a bit of a struggle in trying to achieve quality in whatever we do. But still, I believe we did the very best we could in terms of trying to develop technologies, especially in my domain, which was inspection of nuclear reactors. And I think we did a reasonably good job with the resources available at that time. And as we go through this journey, we'll see that how things have advanced, how things have changed. And if the same set of problems were probably given to us today, we would probably have done it at a much faster rate with probably even a notch higher level of quality. Came the 1990s, and then of course things improved. We started seeing the digital world, and many things improved. We started getting a little more advanced computers, personal computers, the processors became better. So the entire capability to do inspection certainly improved. And I also had a lot of modeling capabilities, which came in the 90s. Also access to digital signal processing, pattern recognition, and many things, which just started evolving in the 90s. Here is a picture on the upper right hand corner, you see of the what we call as the hot cell facility. This is the hot cell facility at the Indira Gandhi Center for Atomic Research, Kalpakkam, where we used to examine the nuclear fuels in an extremely controlled environment by using these robotic arms, which we used to call master slave manipulators. So even at that early in the 90s, we did have these technologies to do a fair bit of inspection with respect to quality of irradiated fuel elements and so on and so forth. So a bit, and then of course, we see where we are today. So quality has always been the hallmark of most of the industries. It is something that you would want to, inculcate in every member of your organization as part of their DNA. And it is something which has to happen if organizations need to succeed, if products need to succeed, and if processes need to succeed. So quality is an inbuilt and an imperative for every single individual and organization around the world. What are the factors which impact quality? There are several factors. I'm not going to go into the whole list here, but it's just not a few of them. It's several, right? Starting from strategy to leadership to management to teamwork to reputation, performance, productivity, and so on. There are several different dimensions of quality when we start looking at a quality in a product, like the one the triangle shows in the right-hand side, primarily focused on performance, features, reliability, conformance, durability, serviceability, aesthetics, perceived quality. So, I mean, the way any individual looks at quality will be a function of what role they are playing in the organization, what is it that they are driving, what is it that they want to achieve. So, the number of factors impacting quality are so many, and that is why it also becomes important to somewhere bridge these various factors in order to achieve the final quality. Also, as the theme of today's quality day is, it's about enhancing and sustaining. Establishing quality methodologies, processes is probably reasonably easy, I would say, not very easy. But when it comes to constantly enhancing, the world is changing every day, every minute. As we want to enhance the quality, as we want to sustain the quality and improve further, that is certainly a much, much bigger challenge. And that needs several elements of factors which need to be taken into account. However, what we are focusing today is three important factors which I believe are very important and which I have personally experienced in the last 3 decades as having a great role in whatever we do in terms of quality of research, quality of the products we've developed, and quality of the processes we develop. And those 3 things are technology, innovation, and processes. So let's talk a little bit about processes. You all would have heard many different processes. However, I believe almost everybody here in the audience has certainly heard of Lean and Six Sigma. And this is one of the very primary and early processes which was used by several organizations to drive quality, quality as a culture. And having been at GE for the last 2 decades, this was something which we had, and we called it as Six Sigma being in your DNA. And this was driven by the then CEO, Jack Welch. As he defined it, Six Sigma is a quality program that when all is said and done improves your customer's experience, lowers your costs and builds better leaders. And he took this on as a mandate with the result that probably GE came to be known as one of the most leading companies driving Six Sigma. And the results were there to see. Somewhere much later came in the concept of Lean, and then it was combined to be called Lean Six Sigma. And what is being practiced today in the company in several of its verticals is what we call today as the Lean Six Sigma. And Lean Six Sigma is an extremely powerful process which can, and an approach, a methodology, a philosophy, whatever you would like to call it, which can really help an organization grow to greater heights, especially with respect to quality. And this comes from somebody who has actually experienced it. So I can certainly vouch for it. So lean, obviously, as you know, creates value for customers by minimizing waste, while Six Sigma reduces defects by effectively solving the process. And combine these and we solve problems and improve process in a faster and more efficient way. There are several different approaches in the Six Sigma, Lean Six Sigma. The two very important are called the DMAIC and the DMADOV. DMAIC is the one on the right hand side, which is define, measure, analyze, improve, and control. And this is typically used when we want to improve an existing product or a process. However, it was GE which brought in the concept of DFSS, called Design for Six Sigma, which essentially meant that we should build in quality into the product rather than trying to test for quality after the product has been built. And that's why it was called Design for Six Sigma. And there we had different steps, some of them being common, but basically talking about define, measure, analyze, design, optimize, and verify. DMADOV or DMADV, as some people used it. And it was the combination of DMAIC and of the DFSS process which brought some of the world's best quality products, be it healthcare, aerospace, power, oil and gas, and many of the other businesses which GE had. And I think the Six Sigma and Lean Six Sigma had a great role to play. And that also did not happen overnight. It took several years to build that culture, and it was virtually being practiced by every single employee in every single activity which they did. The other big concept and approach, which I think in my own experience has helped a lot in enhancing and sustaining quality, has been the use of the concept of technology readiness levels, manufacturing readiness levels, and system readiness level. This is something which came from NASA and US Air Force, as many of you would know, but it's a very structured and beautiful way of actually bringing in quality into everything which we do, and a smooth and seamless handover from the research part of the organization to the manufacturing part of the organization. So we're not going to get into details, but I'm pretty sure several of you in the audience have utilized this and have realized the benefits. So TRL, technology readiness levels, going from 1 to 9, where we start from the basic principles and go to actually proving the system in an operational environment, which then leads to the MRL, or the manufacturing readiness levels, which were again something which was developed to identify the maturity of critical technology elements. It complements TRLs and is usually a very good handshake from the researcher to the manufacturing unit of any organization. And then, of course, MRL goes from 1 to 10 with the different stages as seen here. Not getting into any details here, but I'm pretty sure those who are interested can get into that in greater detail. And also comes SRL, which is a system readiness level, where you kind of combine various components which are manufactured into an eventual system, and that system needs to be ready to cater to the end client or customer. So these, again, addition to Lean Six Sigma, this is something which utilized quite a bit in our day-to-day work, and found that it could be a big enabler for both enhancing and sustaining quality. The third big approach, which is becoming very common in the last few years, though it existed for several decades, is something called design thinking. And this is again becoming very important in the context of quality. So here is a quote from the CEO of Jaguar, which said, if you think good design is expensive, you should look at the cost of bad design. So which means designing is a very important element of quality also, in addition to the research, the manufacturing, and many other aspects which go into building a quality product or a process. So it's a systematic and collaborative, creative problem-solving approach, but very much heavily focused on the customer. It's something which says that you need to empathize with the customer. You need to understand the requirements of a customer much better than what you do today. And that is a product or a design of a product or a process, which is very quality amenable and very high in quality. So it focuses on customer behavior. So here was Lean Six Sigma, came the TRL, MRL, and SRL, and then design thinking. And then when you have to do quality, like I said, you certainly need to be very innovative. You could just stay where you are by doing your following your existing processes, tools, methodologies, and so on. But I think the crux of enhancing quality also is very closely related to innovation. And here is one such methodology which I have been using and GE has been using personally for the last decade plus, which we found very useful, combining two different things. One is to innovate, second is to build into what we do through innovative products. So this is a method called TREES, which is a German acronym. Sorry, not a German, it's a Russian acronym for Theory of Inventive Problem Solving. And this was invented by this gentleman called Heinrich Altschuler, which basically was a combination of taking several patents which existed and finding out what is common between them. And he found that there was something common along a thread along these patents. With that, he came up with something called technical contradiction and physics, which can really help if you formulate your problem in the way which it is shown in the bottom left-hand corner, this way of thinking, where you take your specific problem, abstract it into a general problem, then find the general solution, and then get to a specific solution. It can really give you very innovative solutions to the fundamental problems which you are trying to solve. Of course, we don't have the time to get into detail, but anyone who is interested will be happy to at some point in time give us up, which is a very structured innovation power, and it has strong links with Lean, DFSS, Six Sigma, and all that. So it's a combination of all this which eventually gets you to what we are trying to accomplish in terms of enhancing and sustaining quality. So I just talked about a few approaches which I have personally used, which we in the organization at GE have used, but there are many more. But these I have found personally to be very powerful, and I would strongly recommend to kind of look at it, see potential adoption in your organizations, and take it forward. In addition to all this, the one big thing which many people forget or ignore is the fact that how the standards and regulatory bodies around the world kind of try to help enhance and sustain quality. It is the adherence to standards, development of new standards, and updating of current standards all play a crucial role in quality. Regulatory bodies also key enabler for ensuring rigorous practice and procedures. So there are so many pillars on which quality stands. It is important in its own way, and each one of them can play a big role in sustaining and enhancing quality, whatever it may be. It's a product, it's a process, it's through the organization, and it's a very structured way of combining these and taking the benefits combined out of all that. With that, I kind of move to a slightly different version of quality, which is about product quality and process quality, specifically from viewpoint of the engineering structures, and more specifically in the next several minutes about the domain of non-destructive evaluation and inspection, which many of you are aware of and is a very critical tool and technology to ensure quality of products. So engineering failures, as you can see in the pictures here, is a very common thing. Failures do occur, be it a wind turbine, be it a space shuttle, be it an airline, be it an amusement ride, and bridges, plants and heat exchangers and boilers and so on. And I think and it happens automotive, aerospace, oil and gas, transportation, and so on. So, and this fundamentally happens because of the presence of discontinuities, flaws, or defects, and the damage which occurs in the materials are put into service and the presence of stresses. So there is a need to detect and characterize these in a way where it doesn't impair the end use of the structure, but can still be effectively figuring out the presence or absence of discontinuities, and appropriate action can be taken. We used to be in a very reactive will fail, and then we would like to figure out why. Then we became a little proactive by trying to do many things like structural health monitoring, and now we are getting to a predictive world. And it's natural, there are different types of defects, and so once defects or flaws are there, it is certainly will grow and fail at some point in time. So you can have quality control at the manufacturing stage using several of the NDT techniques. And of course, we also need to pay equal importance to the damages which happen due, be it a simple thing like a car or a cycle or a boiler or a generator, motor, take any kind of structures. It will undergo various kinds of damage mechanisms, including aging, and one needs to take care and try to prevent failure of those much before it actually fails through use of intelligent and smart technologies like structural health monitoring and non-destructive evaluation. And the world is growing, the challenges and needs are constantly growing because which are coming, the kind of composites which are coming in the aerospace industry, the size of the objects, look at the wind blade size, which is the one on the extreme bottom left, you can see is the longest wind blade ever built, 107 meters. And this is for an offshore wind turbine. And as we speak, it's just currently getting installed. So the materials are changing, the shapes and the designs are changing, the size is changing. And of course, there are new manufacturing processes which are coming in, like additive manufacturing. Absolutely new methods, and nobody still fully understands how these materials behave, how to inspect these materials, because these have been created from powders, melting of powders, laser melting of powder. So all these pose huge challenges to the definition of quality when we are talking about product and processes. And NDE, or non-destructive evaluation, is one such methodology which we use to see how product quality can be inspected in a completely non-destructive, non-invasive, and provide adequate information for decision to be taken on the state of the product. And NDE is a cradle to grave technology because we start in assuring quality right from the raw material stage. So a billet of nickel or titanium which goes into a building of an aircraft engine, right from the billet stage of the raw material, it's inspected to ensure that it is defect free. And as it undergoes process and we manufacture the components, assembly, structure, once the engine is manufactured and it is put on a plane, we still do in-service inspection till end of life. That's why it's called cradle to grave, right from the birth of the material to the end of the material. And there are several different, damage mechanisms which have been studied in materials, which kind of create, challenges to the world of inspection to establish quality, not just at the raw material stage, but also at the in-service and in application stage. Again, kind of more of a repeat, but almost at any stage in the production or the life cycle of a component, NDE is used to either assist in product development, sort incoming materials, verify processing, verify assembly, etc. Flaw detection and evaluation, leak detection, the standard things for which NDE is used. And there are hundreds of methods now. What you are seeing here on the screen is just a few methods which are listed. But as of today, there are so many different methods which are either originally new methods or a modification of an existing methodology. And the benefits of NDT driving as a QA management tool is not surprising at all, because it obviously helps in detection of structural flaws, mitigates the operation risks, reduces unplanned machine downtime, and of course detects all kinds of flaws. And so we basically use NDE in two axes. One is the assurance of quality control, of products and systems, and on the other axis, it's asset integrity management, which means once the component is put in service, how do I make use of that? So we'll talk a little bit about the various technologies and the several advancements which have happened. Several of you would be familiar with this thing, the conventional ultrasound testing, very, very popular to inspect all kinds of materials, especially for volumetric defects, has undergone a sea change in the, as the demand for quality of the conventional ultrasound had many limitations in terms of not being able to inspect certain structures, zones of say welded materials, to speed and so on. So from the medical domain, we adopted the phased array ultrasound equipment, which can do inspection very fast. It can give you an image like you can see on the right hand bottommost picture, just like what the doctor gets when he or she does the fetal inspection. The kind of advancements which have happened, phased array ultrasound, and then as the challenges moved to assure quality of tubular structures and pipes, came the advancement in what is called as guided wave ultrasound, which you can see on the upper left-hand corner. And then as we went to inspect composites, we found that we have challenges in terms of trying to, because an ultrasound methodology always uses a couplant, which is either water or a grease or an oil. And when you're doing composite inspection, it becomes difficult to image or do any such thing. And so came what is called as the air-coupled ultrasound technique. That was again a quality requirement from composite inspections. And so came the advancement in this technology and several such things. And it has the ultrasonic testing has moved from manual to automated, is used heavily in lots of structures, be it metallic or composites. Without robotics, we can do pipeline inspections with something called the PIG, the pipeline inspection gauge, which miles collect data on the status of the pipe and help you in maintaining quality of the quality of the pipe and figure out if there are corrosion or damages and so on. The other big thing which happened was that it became very difficult to inspect components when the plant is in operation, and you can't shut down a plant just because you wanted to do a thickness measurement or something. So came the advancement in permanently mounted sensors. So as you can see on the extreme right top picture, which is an offshore rig, and we have valves there, and you can see the elbow joint, which is where a lot of corrosion takes place. So we can paste a transducer there, an ultrasonic transducers, and consistently monitor it for wall thickness, remotely or otherwise. Moving on to the other very popular NDE or non-destructive technique called electromagnetic NDE, which is very popular again in the use for detection of flaws in surface and subsurface, unlike ultrasound, which is more volumetric. The most popular eddy current testing, which is based on Faraday's laws of electromagnetic induction, very popular in the use for tubular structures like heat exchangers and so on, and several advancements from conventional to multi-frequency to pulsed. And all this came because of the need for enhancing and sustaining quality, because newer materials came in and they found out that the regular eddy current could not inspect, say, ferromagnetic materials. That's when they discovered remote field eddy current, partial saturation eddy current. And so the issue of having to inspect large areas then came in. So here is how you can see that technology is a constant handshake with quality. And as the quality demands from the industry keep enhancing, going up, there is a constant need for innovation. And none of these happened without innovation, please remember. And those innovation and technology came hand in hand to provide these answers. Let's talk about a few very new developments in so it was existing, but it became popular in the last 1 decade. Micro, while ultrasonic eddy current is good for metallic materials, but as you go up higher in the frequency, in the microwave frequency zone, now this is excellent for dielectrics such as ceramics, rubber, glasses, polymers, plastics, and so on. And so this is where ultrasonic and eddy current will fail microwave will really give you fantastic results. So again, this was the quality demand from several structures, several industries which used a lot of non-metallic materials to get better and better inspection technology which can find finer and finer defects. So a lot of applications, GFRP tanks, HDP piping, turbine blade coatings on turbine blades and so on. Further extension of from beyond eddy current and microwave, as you go to still very high gigahertz, from 200, 300 gigahertz to 3, 4 terahertz, is what we call as a terahertz ND. This has again been in use for several decades in many of the other industries, including pharmaceuticals, security, communication, and so on. But in the last 1 decade has been again finding a lot of applications, industrial applications, especially with respect to coatings and composites, where you would like to or measure coating thicknesses very accurately and so on. And clearly there is a complementary behavior of terahertz as compared to any of the other technologies as shown in the table below, which makes it very, very popular in kind of use of several different materials, as you can see here, delamination in composites and so on and so forth. So this is becoming more and more popular. The terahertz ND today, tabletop and field ready terahertz equipments are available. Here is an example of how the car industry is used effectively for paint thickness measurements. For the high-end cars, the thickness of the paints is very, very important, and the kind of micron level accuracy which you need is something which you cannot get in any other technology except terahertz. So same can be used for composites and thermal barrier coatings. Pharmaceutical tablets which get coated, they also use a lot of terahertz ND. Modeling and simulation, the finite element modeling and analytical modeling and so on, which in the last 2 just growing in this decade has really caught up. And today it has become so powerful in terms of so many things which you could do to assure quality of your product, without even having to actually do a real testing. The accuracies of these models and the simulation results are so good that, for complex situations, especially even in the inspection domain, you really don't even have to, do the experiment, but get as close a reality, answer as possible. Infrared imaging is another tool where you use the IR image coming out of a body, which is anything about absolute zero, to really again figure out the quality of the components or whatever you are trying to inspect. And it has several large number of applications, and there are so many versions of infrared which now are getting used, like you can see, the various heating methodologies, again very, very popular in composites, foam, and many of the non-metallic materials, but can also be applied to metal. X-ray, which is a very popular technology for everybody. Everybody has probably seen it from a medical field, but in the industrial world, extremely popular because it's like ultrasonic can give you a volumetric defect image. And we have moved from a conventional film-based radiography to a digital radiography, where we use a flat panel detector as is shown here, or something called an imaging plate. And you can really store, archive, do lots of image processing to get better once the product has been inspected. And of course, it has moved to the domain of computed tomography, where you can do 3D imaging and really get accurate, of course, defects, but also a lot of metrology. So, the whole digital radiography has revolutionized the way you can do, X-ray inspections. Talking about some specific structures, wind blade inspection is a very challenging area, huge structure, very big and long, and just when even the wind blade is lying on the ground after manufacture, but imagine the challenges when it's right mounted on top of the wind tower. And every time you have to bring a wind blade down to inspect, it's a very expensive affair. So lots of developments in terms of drone-based inspections and to assure the quality of the wind blades while it is in operation without actually having to remove it. And you can again use several different techniques from ultrasound to and so on and so forth. So that was just a glimpse of have happened in the world of non-destructive evaluation, which directly have a correlation to both, enhancing and sustaining quality when we specifically talk about the industrial world, products and processes. We'll move on to a slightly different thing where we talk about the current revolution which is happening, which is called the Industry 4.0, where we are trying to digitize and use digital transformation for everything. And just in line with Industry 4.0, the world of NDE is also adopting, calling itself NDE 4.0. To that is the recent issue of materials evaluation published by the American Society for NDT in July, which was entirely dedicated to NDE 4.0. So what is it that digital transformation for NDE can mean? Again, please remember, everything which any advancement in NDE will also have a direct impact on the quality of your product and process. It can make quality assurance, quality inspection much easier. So all these in some way are very tightly and closely related in order to get to our final. Digital transformation for NDE could mean you could do remote monitoring through augmented reality and stuff. You can do sensor data fusion. You have many sensors which each gives you different information. You can combine that with machine learning. You can do process monitoring, which means you don't have to wait for the component to be completely manufactured, but can be inspect in process and certify. And of course, predictive analytics. And so automation, which is again a very important pillar for quality, is big drivers are speed, quality, productivity, reliability, and environments specifically. And of course, we all know that one thing is repetitive tasks, if given to robots and equivalent machinery, can certainly reduce some amount of human error. So there are several drivers for automation in ND. Quality inspection in the industrial manufacturing sector. Okay, you can use more and more robots to enhance quality. We can do predictive maintenance, much better, and of course process control. Same thing, with the combination of Industry 4.0 looks at a combination of several things. It could be the robotics, it could be the advanced analytic methodologies like artificial intelligence and machine learning, digital twins, and so on. Combining all these in the world of NDE and inspection to enhance and provide better quality is the goal of NDE 4.0. Again, the operator dependence wherever repetitive tasks have automated defect recognition is something which is becoming very popular to enhance quality, because when in a factory shop floor you have thousands of components being manufactured every shift, and if you are really doing an inspection, 100% inspection, like we do in the case of turbine blades which goes into an aircraft engine, having an operator trying to analyze the radiographic image is a time-consuming task with potential errors likely to happen. So here is a ADR which could potentially do everything in an automated way using the right kind of image processing algorithms combined with artificial intelligence and machine learning. So AI, ML, TL, which is deep learning, all are going to play a big role in how NDE 4.0 helps to enhance quality. And just a few examples here of how signals from various sensors can be automatically analyzed using machine learning models. Identify. I can see the bottom right hand. Very phased array in ultrasound I was talking about is excellent as a methodology, but the challenge still remains about interpreting the signals, and that is where AI, ML, DL can come in very handy. So NDE 4.0 is kind of going to combine all these, which and make learn from the data, give better accuracy, and certainly give you very business value through improved product quality, and of course efficiency, which is something which Industry 4.0 will bring. And to do all that, you have to, cannot always rely on manual inspection. You have to, and the inspections, when you talk about NDE, we do it on ground, we do it in the air, we do it under the sea. So you need, delivery mechanisms like UAVs or drones, which can do inspection in the air. We need crawlers and robots which can do for assets which are on the ground like boilers or turbines. And you need subsea, a lot of oil and gas, subsea piping and risers and so on. ROVs or underwater vehicles to do that. And so robotics is going to be the next big thing which will help enhance quality because of its ability to go into confined spaces, things which a human being cannot do, we can make the robot do it. And that's where the big advantage of inspection robotics, especially it can be used, of course, everywhere, but in large structures like boilers in a thermal power plant or any such, even a turbine where you have to go through small spaces and entry is difficult, or you need extensive scaffolding and other infrastructure to do the inspection. So here's an example of a very novel robot developed by GE, which has an ultrasound sensor, which is a high definition camera, and can do many, many different inspections. So a few videos, in lack of time, I'm not going to show that. The drone inspection is becoming very, very popular because structures at elevation like wind turbines and many others, having a human being climb up there to do the inspection is kind of a very, very tough thing, and you can't do it. Safety is an issue. So with the advent of drones, there's going to be more usage of drones to assure quality of these kind of structures. Less downtime, disruption, of course, very fast retrieval of data, reduced inspection cost, and huge safety gains, here is an example of how the drones with sensors, high definition camera, infrared camera, and even to now they have mounted ultrasound transducers, which can go and actually be in contact with the inspection surface and do those inspections. So the top 3 pictures of wind turbines, the bottom 3 pictures are they're flying a drone inside a boiler, a thermal coal boiler, and so no human entry is required. It can, and there are, unfortunately I've not put in that image, but if you see the quality of image, it's so fantastic. The quality of images which you can get without human entry itself. The amount of time, typically they give you 15 days to open and shut the boiler after inspection. You could now save almost more than 60% of the time by finishing this boiler inspection in like 3 days, 4 days, if you use combination of robotics and drones. And of course, the data you get we can always do automated classification using several algorithms and so on. So this is an aerial picture taken by the drone and classification algorithm corroded areas in various kind of reactors. The next big thing which is coming our way, which can really again help enhance and sustain quality using the concepts of Industry 4.0 and NDT 4.0 is digital twin, which is nothing but a digital replica of a physical asset. And this is the next big revolution which can help enhance the quality to some unimaginable levels, is what we believe, based on some limited experiences which we have already had at GE, applying it to aviation and to the boiler and some of the other assets. We already see a huge benefit which can come from the adoption of digital twin, where it's a combination of the physical asset with the digital version of that asset, where you can superimpose all the operating conditions and really get in a very predictive manner how that component, how the structure is going to behave. And it's the data which you get from the real world asset transformed and superimposed on the digital asset, which connects both the worlds. And then, of course, you all have seen and heard about augmented virtual mixed reality. That is going to revolutionize the way inspections get done. And when that revolution happens, it will enhance again quality in a totally different manner, with more operator confidence, more operator guidance, and so on and so forth. So, in short, we talked about different things. We talked about processes. We talked about Lean Six Sigma, design thinking, and many other things. This thing TRIZ for innovation. We talked about use of the TRL, MRL, and SRL. So somewhere it's a synergy between all these, to eventually get to what we are talking about, transforming, enhancing and kind of sustaining quality. And here is just an example of the ND 4.0 kind of synergies which are going to happen. And rest assured that each one of them will have a big role to play in enhancing the quality of our products and processes. So in summary, quality in industry and elsewhere is an inherent need to ensure quality, productivity, reliability, safety, and customer satisfaction. Ensuring quality is a must, but the constantly dynamic and changing ecosystem also demands the need for enhancement and sustainment of the same. And there is only one way we can do achieve all this, is to innovate, evaluate, adopt, implement technologies and processes to move forward. It is a combination of all this. It's not just any one element which will take you forward. So we have to keep our eyes and ears open. We have to adopt everything which is happening in the surrounding adjacencies. We all have a core on which we work, but several of the times we forget to appreciate and adopt the kind of developments happening in the adjacencies. And Industry 4.0, ND 4.0, Quality 4.0, as they eventually will come together, is all just one such way of synergizing, of integrating everything which is happening in the various domains to finally, make this world a very safe place to live in. With that, I would like to thank you for a patient hearing. I do hope some of the elements, this is a vast topic, so I've just touched bits and pieces of it based on certain personal experiences and personal knowledge of where some of the big corporates and many others are trying to go, and eventually at some point in time they all lead to single word quality. With that, thank you once again for this privilege and honor to speak to this audience, and I would like to thank you once again and wish you all the very best on this quality day at the Vikram Sarabhai Space Center. Thank you very much.